Hi, everyone. Today we are doing lesson 4. We're learning about mutually exclusive events. So if you'd like, you could copy these notes down into a notebook, or if you prefer, I've posted a PDF of like a lesson sheet, so you could print that off and use that as like with a bit of structure. Whatever you'd like to do, whatever your personal preference is. Today we'll be using Venn diagrams quite a bit. Like most of us have seen a Venn diagram or used some before. Here's just a few like funny Venn diagrams I found kicking around the internet. So I found that hipster Venn diagram pretty interesting. The idea being in the middle is like things that like overlap that are like in both sets. This one's my all-time personal favorite. There's so many levels going on here. Blue and yellow mixed make green. The beaver, the duck-billed platypus. You take a guitar with a synthesizer and you get whatever that instrument is in the middle. But anyway, we're going to start off today's lesson with some examples from a standard deck of cards. I know not everybody plays cards, so just really quickly going over what they're about. A standard deck has 52 cards in total. And every deck has 4 suits. So you can see the suits are clubs, spades, hearts, and diamonds. And in every suit, there's 13 different like types of cards, I'll just say. 13 cards in a suit. So you've got your ace, and then the numbers 2 up to 10, and then what we call the face cards, because they have a face on them. Makes a lot of sense. So these are the face cards: a jack, queen, and a king. And again, there's 52 in total. So we may reference this visual today as we do some examples. So let's move on. Let's do a Venn diagram together, showing clubs and spades. I'm just kind of seeing how many are in each set. So with the Venn diagram, so we have a circle. You can use any shape really, but usually circles are used for sets. And a big rectangle is used to represent the entire sample space. And in a Venn diagram, we just kind of populate each shape with how many objects are in that space. So we know there are 13 clubs. We know that there are 13 spades. And these two circles are separate because there's no overlap between them. And then in a deck of cards, there's 26 cards that aren't clubs or spades. They don't belong in each. And you'll notice that 13 plus 13 plus 26 is equals to 52. All cards are represented in that Venn diagram. Because a card can't be a club and a spade at the same time. So those two sets were completely separate. But here we'll do another one for diamonds and face cards. And here we're going to have a bit of overlap, because if we look at the diagram, there are 3 cards that are both diamonds and face cards, because the diamonds are in this row, the face cards are in that row. So there's 13 diamonds and 12 face cards, but there's 3 that are both. And so the way that we show that in a Venn diagram is we say there are 3 cards in that overlap. We know that there are 12 face cards, 3 are diamonds, and that leaves 9 outside that are face cards but are not diamonds. And then there are 10 cards that are diamonds and that are not face cards. And if you add those up, that's 22. That leaves 30 cards in the rest of the deck that aren't a diamond or a face card. And so that's how you do a tree diagram when you do have some overlap, and it is worth checking. 30 plus 10 plus 3 plus 9 is indeed 52. All right, so today we will come back to Venn diagrams in a second, but what that kind of motivated was this idea of mutually exclusive events. So when we're calculating the probability of one event happening or another, so it's important to really carefully count the outcomes. So if we were interested in calculating the probability of drawing a club or a spade from a deck of cards, like that's actually not too bad because there's 26 cards that are a club or a spade. It's 13 plus 13 out of 52. But in the second case, I'm just going to erase that. In the second case, if we were looking for like the probability of drawing a diamond or a face card, like if we just think about what would happen if you just added up the number of diamonds, which is 13, plus the number of face cards, which is 12, that gives you 25. And 25 is actually not the probability of drawing a diamond or a face card, because as you can see in here, 10 plus 3 plus 9, there's only actually 22 cards that are either a diamond or a king. So you have to be really careful counting these outcomes, and that's where today's lesson comes in. We're going to get some experience doing that. Just erase these for later. All right, let's move on. So yeah, as I said, it's easy to do when events are completely different, like clubs and spades. Events like clubs, drawing a club and drawing a spade, are mutually exclusive. We're saying they're mutually exclusive events. They are events that have different attributes and cannot occur simultaneously. They can't occur at the same time. So they're different attributes and they cannot occur simultaneously. You can't draw a card that's both a club and a spade at the same time, completely different. And conversely, when two events have outcomes that overlap, like the diamonds and the face cards, we say they are non-mutually exclusive. So in the last example, we had 3 cards: the Jack of Diamonds, the Queen of Diamonds, and the King of Diamonds that were in both categories. So those two things could happen at the same time. I could draw a card that is both a diamond and a face card. So that's the difference there. Let's do an example. So really a pretty simple one. So a picnic basket of sandwiches contains 3 ham sandwiches, 2 turkey, 1 chicken, and 4 egg salad sandwiches. We'd like to know what the probability of reaching in and randomly choosing either a ham or an egg salad sandwich. So maybe those are your favorites, you only the other 2. What's the chance of randomly getting one of these that you like when you reach and dive in? Well, because these are mutually exclusive, these are mutually exclusive events, right? I can't draw a sandwich that's a ham sandwich and an egg salad sandwich at the same time. So I can write it this way. The probability of getting a ham sandwich or egg salad, well, if they can't both happen at the same time, I could just find the probability of getting a ham sandwich and find the probability of getting an egg salad sandwich and just like add them together. There's no overlap there. So in total, we have 3 ham, 2 turkey, 1 chicken, 4 egg. That's 10 sandwiches all together. And so the probability of getting a ham sandwich, well, that's 3 out of 10. And the probability of getting an egg salad sandwich, there's 4. So there's 7 of those 10 sandwiches that would satisfy this criteria. We've done our first problem. So it's quite easy doing problems, like one thing or another with, go back for a second here, with mutually exclusive events, because you just have to add those together. It's pretty straightforward. Why don't you try this one? So take a moment and pause the lesson here. Try this one at home or on the lesson sheet if you have it. and unpause it when you're ready to take it up and see a solution. All right, so here we go. So we have a cooler with a bunch of juice bottles. So if you kind of look at all the possibilities, 3, 5, 3, and 4, that makes 15 bottles altogether. And we're looking for the probability of reaching in and randomly choose. So we're not looking in, we're just randomly reaching in, not looking and choosing apple or grape juice. And again, these are mutually exclusive events because you can't get some juice that's both apple juice and grape juice at the same time. So because they're mutually exclusive, we can just, find the probability of getting apple juice or grape juice. We can just find the probability of getting apple juice, find the probability of getting grape juice, and add them together. And 5 of 15 are apple, and 4 of 15 are grape, and that makes 9 out of 15, or in lowest terms, 3 out of 5, or 60%, or however you want to express that. Remember, there's many ways to express probability: fraction, percent, or decimal. One thing to notice in this question here is, maybe you're wondering, well, the probability of getting apple was 5 out of 15. Why didn't I put that into lowest terms? Well, in cases like these, when adding probabilities together, it's actually much easier if they have the same denominator. That makes adding those fractions a lot easier. So it's often in your best interest for these kind of questions. Keep them as the same denominator. It'll make your life a lot easier. All right. The principle that we used here is called the additive principle, or the rule of sum. And it says that the number of, and this is for mutually exclusive events, the number of elements in set A or set B is just the number of elements in set A plus the number of elements in set B. So just to draw a little visual of what that looks like, it's like our clubs and spades example, where you have set A and you have set B, and they're completely separate. So, just going back to, maybe I'll do this. So the number of, I'm going to do my best at drawing. There's a club or I picked the hardest suits to draw. The number of cards that are a club or a spade, because those are mutually exclusive, it's the number of clubs plus the number that are spades. And we already did this one. We just didn't call it the additive principle. That was 13 clubs and 13 spades, add them together, get 26. So that's the kind of the formal name for what we did there when two events are mutually exclusive. Now, I particularly like using the term rule of sum, but depending on the resource you use, or depending on the course you take in university, your teacher professor might refer to this as the additive principle. So from here on, I'll kind of usually call it the rule of sum. Let's do another example. So here, a number of actors have played James Bond over the years. Daniel Craig is actually, he's in his 4th or 5th one now that's recently coming out, but this table is a little outdated, but no big deal. This is just a collection that Raleigh has, and it's sorted by actor. So Sean Connery's been in 6 Bond movies, Roger Moore's been in 7. You can see the breakdown there. So let's say that he randomly picks a movie on a Friday night, and maybe Sean Connery and Timothy Dalton are his favorite James Bond actors. We'll denote those two sets by C and D. What's the probability of him picking a Sean Connery film or a Timothy Dalton film? So let's go through this one together. So using what we just learned, the probability of him picking a Sean Connery film or a Timothy Dalton film. That might just to reemphasize, these are mutually exclusive events. You can't have a James Bond movie where Sean Connery is James Bond and Timothy Dalton is James Bond. They are mutually exclusive events. And so to get that, we just kind of use our additive principle with probabilities. So the probability of getting a Sean Connery or Timothy Dalton is just the probability of picking a Sean Connery film plus the probability of getting a Timothy Dalton film. And if we go back to the table there, we can see that in total there are 22 total movies, 6 Sean Connery and 2 Timothy Dalton. So that would be 6 out of 22 plus 2 out of 22, 8 out of 22. That's a chance of getting a movie that's either Sean Connery or Timothy Dalton. If you'd like, you can reduce that to the lowest terms, 4 out of 11, or get that as a probability or percentage. Works out to about 0.36 or about 36%, roughly. Not exactly, but roughly. All right, so we've done a lot of mutually exclusive event problems where there's no overlap, so we just add probabilities, very straightforward. In other situations, like the one we looked at earlier, it is possible for different events to happen at the same time. So like our diamonds and face cards example. So here I'm going to let n of d represent the number of diamonds, and an f is going to represent the number of face cards. And so if you check this out, you've got 13 cards that are diamonds. The number of face cards is 12. And if you add those up, you get 25. But if you were to actually physically count all these cards up, there's only 22 in this diagram that are diamonds or face cards. So if you just use that rule of sum, it doesn't work for non-mutually exclusive events because you're counting some things twice. So that last sum included 3 cards belonging to both sets. We talked about that earlier. This is the Jack, Queen, and King of Diamonds. This is an example of non-mutually exclusive events. The formal definition is that there are different events that can happen at the same time, like getting a diamond and a face card. That's possible. So if you wanted to obtain the correct number of diamonds and face cards, you'd have to do this. You'd have to take that 25 that we got earlier, and you'd have to take away 3. You have to take away that overlap. In this case, there was 3 cards, and there are 22 cards that are diamonds or face cards. So that's the idea. It's because with non-mutually exclusive events, some things counted twice, you're going to have to subtract them off once. So this is known as the principle of inclusion or exclusion. So this actually works for mutually exclusive events too, because if 2 events are mutually exclusive, this number of events that are in A and B would actually be equal to 0. But for non-mutually exclusive events, we use this principle of inclusion exclusion. So it says to get the number of elements in set A or set B, you add the number of elements for each event or each set, but then you subtract the overlap. So you can see in this diagram here why that is. You can see that events A and B overlap each other. And in terms of like just an area, you'd be counting that area twice. So you have to subtract it off one time, much like the diamonds and face card example. So let's do an example with that. So in a room with 30 students, so 10 play basketball, extra A there. 15 play volleyball, but 7 students play both sports. So what's the probability that a student that chose them at random plays basketball or volleyball? You can't just add 10 and 15 because you're going to be counting 7 students 2 times. So representing that, maybe if you want to do this quickly, we can actually make a quick Venn diagram to show this, and it's not a bad idea to do initially. So two overlapping sets, because these are non-mutually exclusive events, they can both happen at the same time. So I'll call this set B for basketball. Excuse me. Call this set V for volleyball. And starting from the inside out, I know that 7 students play both sports, 10 play basketball, and that means that 3 of them would just play basketball, plus the 7 who also play volleyball makes 10. And 15 play volleyball, so 15 minus 7, 8 people would play just volleyball. And if you add those up, this isn't part of the question, but there's 18 students representing that diagram. That would leave 12 students that don't play either sport. So now we can see the probability that a student at random plays basketball or volleyball. Let's do it this way. If you follow along, the probability of a student playing basketball or volleyball, well, using our definition for theoretical probability, it's the number of students that play basketball or volleyball over the total number of students, or the number of elements in our sample space. And we'll use our principle of inclusion exclusion here. So this is the number of students who play basketball plus the number of students who play volleyball minus the number of students who play both basketball and volleyball. And we know all of those things. So let's plug these in, get our answer, then compare that with our Venn diagram. So the number of students that play basketball, 10. Number of students that play volleyball, 15. But 7 people play both. We've counted them twice, so we subtract them off once, and there are 30 people in the class. So that's 25 minus 7. That's 18 out of 30, or 3 out of 5, or 60%, whatever you choose. And that actually jives with our Venn diagram. If you have a look at the Venn diagram and ask yourself how many students are inside the B and V sets, 3 plus 7 plus 8 indeed does give you 18. So you could do this problem using a Venn diagram. We also did it using our definition of theoretical probability and using our principle of inclusion or exclusion there. A quicker way to get at the probability of 2 non-mutually exclusive events is actually just to use that principle of inclusion exclusion, but instead of the number of elements in the set, you can just actually add the probabilities and subtract the probability of the overlap. It can help you do a question a bit quicker. So let's do that. You can do it with me with this question here if you'd like. So here Miranda is part of a gift exchange with 24 other family members and friends. So of those 24 members, 10 like to ski, 12 like to cycle, 6 of them, there's an overlap, like to ski and cycle. So those are non-mutually exclusive events because they can both happen at the same time. A person can like both of those. So if she picks a name, what's the probability she'll get someone who actually likes one of those 2 things? Well, we can use our previous, the shortcut we saw for probability. So the probability that somebody likes to ski or cycle is the probability that they like to ski plus the probability that a random person likes to cycle minus the probability that someone likes to ski and cycle. And all these things are pretty easy to calculate. So 10 of the 24 like to ski. 12 of the 24 like to cycle. That's a 22, but that would count the 6 people twice who like both. So we have to subtract off that one time. And keeping the denominators the same makes it easy to add these. So you get 10 plus 12, 22. 22 minus 6 is 16. You get 16 out of 24, or a 2 out of 3 chance, or if you prefer, about 66.7%. All right, so hopefully after this lesson, you can identify whether 2 events are mutually exclusive or non-mutually exclusive. Finding probabilities of one event or another is fairly straightforward. When the two events are mutually exclusive, you just add them. But in the case where they both can happen at the same time, they're non-mutually exclusive, you will have to subtract the overlap. So your next steps is nothing to submit today. I just want you guys to just do some practice, get used to this idea. I posted a PDF of some practice problems to the classroom. You should try questions 1 to 8 and 11. Answers are provided for those. On that sheet, questions 9 and 10 are a little bit more open-ended, and feel free to give those a go if you'd like. But yeah, this concludes our fourth lesson.